Okay, so I want to talk about like kind of going to the next level beyond what is usually referred to as smart contracts and like enabling general purpose computation on the blockchain and what is needed for that. And by general purpose, I mean in the sense you talk about general purpose programming languages, for example. So really having arbitrary kind of software running on top of a blockchain technology. So let me first take a step back and like, what are smart contracts? Actually, I guess most of you know really, but just to recap and kind of walk through what the limitations are from my perspective. So I assume most of you know that the term was coined like a long time ago by Nick Chabot, and with a more specific meaning, but nowadays really it's more like a fancy name if you want for a specific class of domain-specific languages. And the kind of common properties of these languages are that they run on a blockchain, that they usually have some notion of funds and describing ownership and transfer of that. And also usually that they have some kind of additional functionality that you don't usually find in ordinary programming languages that is specific to the blockchain context. And that's fine, but of course they also usually come with various limitations. So what are the limitations of smart contract languages as we typically see them? And I have a list here, and not all of the things I mentioned apply to all of the smart contract languages, but there's like, they usually have some of them at least. So first of all, usually the computational power they provide is somewhat limited. So that means that they're lacking certain data types you would expect from an ordinary programming language, maybe like most prominently something like floats. They often shy away from providing. They usually have fairly conservative set of control constructs. So you have maybe loops and stuff, but usually you don't have things like exceptions, continuations, or like the more modern things, generators you would expect from modern programming languages. And there is this notion of gas that kind of cross-cuts the entire semantics. So, and that is usually bounded by a pair message. So the caller into a program has to provide the gas, and that can be used up while you compute, which also means that it's not easy to amortize algorithmic costs across multiple calls. So if you, for example, have more complicated data structures, like some trees that you want to rebalance at certain points in time, then there's no easy way to do that because, well, some unlucky person will have to pay the entire cost for the rebalancing all of a sudden. Likewise, storage is pretty restrictive and expensive as well. So usually storage on or state on the blockchain is organized in certain ways, like usually some kind of Merkle tree, and this kind of shines through more or less to the language. And usually you have to organize your data in certain ways, or it costs to organize it in less restricted ways.
Sorry, Andreas.
Yeah.
One moment. If you are still on the title slide, then we see the same slide that you see. If you are not on the title slide, then we are delayed.
Oh, no, I'm not on. I'm like 3 slides in.
Yeah, that's what we got the impression.
Oh, okay.
I think I'm not exactly sure. I've had this recently with one of the Zoom tools and one of the platforms.
Oh yeah, it says sharing is paused. I don't know why that is. Okay, let me resume sharing, which doesn't do anything.
Maybe we have to stop sharing and then maybe start again.
Yeah, try stop sharing.
Okay.
Computer science approach to everything.
Yeah, sorry about that. Interesting. So where did the Zoom?
Before we actually saw the edit mode, so that for sure will work.
Oh, okay. Yeah,
but I mean,
have seen that
before you really started. Now we see the edit mode.
Yeah, sorry, that was the wrong window I shared there. So you see that.
Yeah, with your mouse.
But when I play, you don't see it.
Well, now we go to the next page.
Yeah, try the next slide.
Yeah. No, it says sharing is paused. That is weird. So this used to work in Zoom. I've used it a lot of times.
Yeah, but this is, they do updates and then it no longer works.
That's annoying. Okay, so I'll probably have to do it from here then. Okay.
Just click the thing on the right away and then we see about as much. If you can get rid of the...
Yeah, unfortunately, animations won't work then.
Do you have two screens? Andreas, do you have two screens? Because at times Zoom does weird things. If maybe...
Okay.
I have only one screen.
Say that if you know the solution.
Let's work in let's do in edit mode, because otherwise we're gonna use all the time.
No.
Yes.
Okay, so I won't have animations unfortunately then, but okay, it has to do without. So yeah, I already was through that slide, and I was talking about limitations of existing smart contract languages. I think I had that slide, and I was somewhere here. Right, so the storage model is another kind of thing that is relatively restricted and very expensive in existing blockchains. So yeah, I already talked through the first point. I think the other thing, it's really expensive. So there is this one web page that tries to compute the cost of storing like 1 gigabyte of data on Ethereum, and a few days ago at least that was around $100 million. It's probably cheaper now because the price of Ether crashed, but it's still like way out there, right? So it's not realistic to store large amounts of data on a blockchain like Ethereum. And then there's the thing that, yeah, so some implementation details, low-level details of the underlying blockchain often shine through in the programming model, and some of these things you have to use to solve certain problems. So you have to talk about block IDs or block height. You often use block time as an approximation for real time. Something like payments have to be made a primitive concept usually, and other things as well, like certain crypto primitives, because there is no good way to implement them in terms of the language or VM provided. And it's usually kind of a closed ecosystem. So most of these chains have one, maybe two like dedicated languages that can run on it and that provide the user experience. And there is no real diversity. You cannot run your own language or like any ordinary language in quotes, and they cannot or it could not interop. Also, you cannot easily talk to the outside world in any real way. And there is, in at least the more traditional ones like Ethereum, there is like the assumption that all execution is synchronous, right? So you have like a call tree and you can abort that entire call tree and you basically block until that has returned. And that also has problems I'm gonna talk about. And what that means altogether is that basically there's no real way to port conventional software to these platforms. You cannot reuse existing programming languages or their compilers, and you cannot reuse existing libraries. So you have to redo everything and kind of integrate it into the platform as a primitive, and there is no real OS on it, like typical traditional OS notions you can't even emulate properly without making them primitive in some way on the platform. So what I want to talk about is like, how can we overcome these limitations? And basically, well, as usual in computer science, the kind of solution is on a very high level is some form of abstraction, right? And this abstraction is that we basically want to emulate a more conventional computational model on top of a blockchain. And we want to, as much as possible, encapsulate and hide all the kind of blockchain-specific implementation details so that programmers and developers and software in general doesn't have to deal with all the like idiosyncrasies of blockchain, so that you can just program as if you were programming a native application or a web application, maybe, if you prefer. And in this talk, there are many things you have to do here, but I want to talk about three main ingredients from my perspective, and I will walk through them in turn. So the first one is that you want a kind of universal machine model, right? You don't want like a blockchain specific VM, you want something that is really more like conventional hardware. And The obvious kind of thing nowadays, obviously I'm biased, but what has been used in many similar circumstances now is WebAssembly, because WebAssembly is this kind of abstraction. It's essentially abstracting a CPU. So you probably have heard about WebAssembly, but let me briefly kind of give you the elevator pitch of what it is. So it's a virtual instruction set architecture. So it means it emulates kind of like a sort of instruction set like a real hardware CPU has. It can be sandboxed. So like when you have a module, it cannot at all access anything from the outside world, from the host. And the host is in full control of that. And it is designed in such a way that's actually embeddable anywhere in any software system. So despite the name WebAssembly, it's actually, my slogan usually is, it's neither web nor assembly. And it has been used, as you probably have seen in the past, in various other environments already, including blockchain. Multiple blockchain projects use it already. So another way to put it, it's really more like a low-level virtual machine, if you want. Emphasis here in a way on low level, because that sets it apart from most other virtual machines. So it's low level in the sense that it's really similar to what hardware provides. And often it's also just abbreviated to Wasm. And I have to insert my usual like pet peeve here. It's spelled Wasm all across the internet, but that's actually not the correct spelling. It's not an acronym. So the correct spelling as per the spec is Wasm in lowercase, just as an aside. So what are the main properties of WebAssembly? Why is it interesting? So it's a portable code format if you want. It's efficient and it's compact. And as I said, it abstracts modern hardware. It's not an abstraction of a programming language like many or like well-known conventional VMs like the JVM, for example. That is really a thin abstraction over Java, the language, whereas WebAssembly is an abstraction over the commonalities of modern CPUs. And it's also another big advantage, especially in the kind of blockchain space, is that it's fully formally specified. And in fact, this specification is machine verified. And I will get back to that shortly. So when we designed WebAssembly, there were various constraints and design goals that we wanted to achieve or meet. And you can kind of sort them into two categories. The one is in semantics. So there are various things we wanted to have for its semantics. And the other is representation, which means that the code should be like small, for example. And I will not walk through all of them. Just want to point out that there are a couple here that are particularly relevant to something like blockchain, where you care about correctness and things like that, and determinism. So these three perhaps the most interesting one in the context we're talking about. So determinism is an interesting one because unlike most other programming languages or VMs, WebAssembly is really fully specified. There's no undefined behavior, almost no underspecified behavior. And that includes even things like floating point arithmetics. So there's only one tiny exception, which we kind of had to give in to, which is where the IEEE floating point standard failed us, and that is the representation of nans. So unfortunately, IEEE does not specify the bit patterns that should be produced for nans, and nans can have many, many different bit patterns. And whereas actual CPUs disagree on what they do. So we went through various iterations of trying to nail it down. It's still very restricted what a WebAssembly implementation can do, but there is a certain amount of non-determinism there where we allow a certain set of bit patterns to arise. But this is really, and the reason we allow it is because like on native hardware, you would lose quite a bit of performance if you required every VM to normalize it. But there's nothing preventing a given VM or ecosystem to actually require this normalization, and it's very easy to implement. So you can actually run WebAssembly in a fully deterministic way with just adding NaN normalization in the right places. And yeah, that's what you will have to do. And then you have something like floats on blockchain if you want. And the other interesting thing is that, yeah, what I already mentioned, there's a complete end-to-end formalization, mathematical formalization of the WebAssembly, not just semantics, but also the binary format and the text format and the validation, everything. And that's using like basically state-of-the-art techniques from programming language research. So all the nice things that the PL community has developed over the past 3 or 4 decades. And on top of that, by using these kind of standard paper techniques, we also were able to machine verify it and use all the techniques for actually using theory improvers to validate the semantics, improving things like soundness of the type system. And there are a number of papers myself and some co-authors published on the specification and the mechanization of the specification. And on top of that, this formalization is not just like some paper artifact we created, but it's actually a central part of the official WebAssembly standard. So it's really the centerpiece of the whole definition of WebAssembly. And there's a very rich proposal process for extending WebAssembly, and one central requirement there is that you actually extend the formal specification. So you're not allowed to extend WebAssembly without adapting the formalization. And just to give you a quick glance, so this is like a page from our PLDI paper, and this is the entire operational semantics of WebAssembly. It's like one page in the paper, and one kind of nice side aspect of designing something in lockstep with the formalization is that you end up with much cleaner design and semantics. And like this one page set of rules is perhaps evidence, or at least indication of that. So yeah, so WebAssembly is nice for our purposes. So here's a little summary. It's like efficient, but also safe. It's deterministic, and it can support like a variety of programming languages already. So there are many compilers being built for WebAssembly. Most of them are maybe not entirely mature yet. It's still a very young technology, obviously, but the set of languages it supports is increasing constantly. And at the same time, it's like standardized, and there are multiple, like at least half a dozen different implementations you can choose from if you want to build something with a WebAssembly VM inside that you can just embed. So depending on what your requirements are, there's a wide choice. And having this formal semantics supports a rich verification. So like I mentioned, these mechanized formalizations, and they have already been hooked into existing frameworks for verification, and other researchers have looked into that. And finally, one important part is that, well, WebAssembly is a very rich ecosystem and a growing ecosystem. So there are various libraries you can use and various movements to like make it an even richer ecosystem. And one is called Wasm, which is kind of like a collection of libraries and APIs that can do things like emulating certain OS functionality that you might not have on the platform you're running. So one of the primary platforms for WebAssembly obviously is the web, and that has to some extent a similar problem. So certain OS primitives don't exist there. So they're also interested in being able to emulate certain things, and we can like basically directly rip off that work if we want, or some of it at least, to benefit from that. So that's like the first ingredient. The second one is advancing the model of state. And one possibility here is that you actually implement something that is called orthogonal persistence. So before I explain what that is, let me say a little bit about the WebAssembly memory model itself. So we are running WebAssembly code, and WebAssembly has a certain memory model, and that's basically that its state, or most of it, I'm ignoring some detail, like minor details here, consists of what we call the linear memory. And the linear memory is just like a big raw array of bytes, right? Similar to a physical address range. And you can access that, you can random access that. This access will be bounce checked, so it's safe, but it's otherwise random. And there are instructions for multi-byte access to read like a word, a long word or a float or something like that from random addresses, which will touch multiple bytes at the same time. And this memory can be pretty large, so it can grow. You can grow it dynamically up to 4 gigabytes in the current version of WebAssembly. So it's like a 32-bit address space. And there's currently a proposal that has advanced quite far already that will extend that to a 64-bit address space, which means that on realistic hardware, you will have actually 48-bit addresses, which is, I think, what current hardware provides. So that would give you like 256 terabytes. And so this is really the main thing it gives you. And on top of that, like something like a language runtime then just rolls its own memory management scheme, whatever it wants to do there. So either you implement a low-level language and provide something like a simple malloc primitive and a heap for that, or you do something more high level where you implement a garbage collector inside this memory. And you can have many of these things at the same time, right? You can separate different memory areas for different and use them for different things if you want. So this is completely up to the implementation. It's not something that the VM itself will prescribe, which enables porting existing languages because they can just use their existing implementation as they use on native hardware and run it here with some adjustments probably, but in principle. So what does orthogonal persistence mean? Well, you now have to talk about, like, you have this big piece of state. What do you do with it? How do you deal with that on a blockchain? And what you really want to achieve is that you give this illusion that this memory is just there. So you actually want to just keep it alive across calls into your contract or whatever you want to call that. And give the illusion that this thing is just a program that's running forever and its memory just stays there. So that means that compilers don't have to do anything specific. They just have to do their usual in-memory management story. And as a programmer or a language, as a developer, you don't have to deal with something like external storage concepts if you don't want to. You can basically just have in-memory data structures. If that's what you prefer. If that's not what you prefer, you can emulate something like external storage or like databases, file systems, key value storage, or these things. You can emulate them as a library, right? So that runs again in memory. So you could have another WebAssembly module potentially that you link to that implements one of these things in memory, at least conceptually. And that sounds pretty great, but how would you actually implement that? And now I kind of regret that I don't have animations here, because now you see all the spoilers already. So first question,
you can try again, but you have to probably restart the whole sharing.
Yeah, it doesn't matter. It's just don't look, So the first question you would probably ask is like, how the heck would I store 4 gigabytes of memory in a block, right, on a blockchain? Well, obviously you don't, right? What you actually store in the chain is just like, usually, as usual, the ingress messages that were received, and then basically a hash of the diff of a state. So in whatever way the contract has touched the state. But then the second question that comes, like, how do you possibly diff 4 gigabytes of memory? And this is where it becomes more interesting. Again, obviously you don't, and there you use more interesting like implementation techniques, in particular virtual memory techniques, so that are provided by modern hardware. So you partition this entire linear memory or the address space that has been allocated so far into small pages, like let's say 4 megabyte pages or something, and then you rely on memory management units in your CPU to tell you which pages were actually modified, so which pages are dirty. And then you only have to compute the hashes of these pages. And usually those are very few, and you can do that rather efficiently. And on top of that, of course, somewhere in a replica, so in a node running for running this blockchain, you obviously have to represent this whole memory somehow, and maybe have to save it. And another clever thing you can do there is you can just use memory map files, so something like mmap, to actually have the memory in a file and just cache that there. And you just have this file lying around, and if a contract hasn't been used for a while, then you can just unmap it and later remap it. And furthermore, to implement something like rollbacks that you need if something fails in a contract, right, like you run out of gas or something, you can do quite efficiently by using file systems that support copy on write. So where you can copy a file for basically constant cost, and it's only getting copied and only parts of it ideally when you start to modify it. And then you can always return to the old copy efficiently. And often you don't need to actually copy anything. So that is a couple of clever tricks, implementing which requires quite a bit of engineering, but in principle, you see the idea. And then the overall benefits of this is like, yeah, applications now basically behave like very ordinary programs. They're just running forever in a virtual sense. And you can continue using your conventional memory management techniques, or the implementation of your programming language or whatever you have there to run your programs can do that. And of course, there's kind of like a small caveat there that when you use the memory in a very like unorganized way, then this will still be expensive. Like you're gonna touch a lot of pages, and that will make it more expensive. So you will still benefit from kind of optimizing for this environment, but you don't necessarily have to. And if you're not using a lot of memory at all, then it doesn't really matter. Yeah, you can implement external storage in memory as libraries. And what has been claimed here is that with techniques like these, you can make memory cost as low as like $5 or $10 per gigabyte. And I should mention that orthogonal persistence is like an old idea, and it has one big caveat. One big disadvantage is that you somehow have to deal with upgrades in some way. So if all the memory you have is like your live in memory data structure or memory layout of a process, how would you possibly upgrade a program if you want to update it to a new version, right? So at that point, you have to do something about the data structures, because the updated version might have a different data layout. So in general, it's not easy to reinterpret the existing memory image with a new code. And so either you have to serialize it at that point, like convert it in some well-defined representation, or you have to make sure that your application, your implementation is stable in a certain way, guarantees that memory layout doesn't change across versions. And you can have mixtures of these techniques. You can also have different areas in memory, ones which are stable, ones which are volatile or something like that. But this is the one point where you have to be careful, and where this kind of technique can backfire if you're not. Okay, and then the third ingredient I want to talk about is like a process model. So what are actually programs in such a system? And the solution I am suggesting here is one that is not new either, and that has already been suggested numerous times in the blockchain context, is this whole concept of actors. And I'm talking here about a distributed process model. So why is that? And for that, I need to talk about sharding. So for this whole blockchain thing to scale, at least if you want to do general purpose computation, then you really need sharding, right? Otherwise, you have this bottleneck of a single chain, and that obviously won't scale. But if you have sharding, you also want to be flexible in how that is used. So you want to be able to communicate more or less transparently between different shards. So if you have programs running on one shard and one on the other, then you still want them to be able to communicate with each other, ideally as if they were on the same chain. And furthermore, you even want to be able to move applications between chains. So for example, to do load balancing or things like that. And that implies that any cross-shard communication, or actually cross-application communication, is interchain messaging, right? And at that point, you have to absolutely assume that there is going to be some latency in communication, and the latency is generally unpredictable because you have two different chains talking to each other, so you don't know when then that will finalize the call, and you cannot assume global time anymore. That's just not a concept anymore at this point. Each chain has to do its own thing, build its own blocks, sign them separately, and they can talk to each other, but there's no global synchronization anymore. So what we're talking about here is you basically have a concurrent setting. So each chain is running concurrently to the others, and it's a distributed setting because the chains are kind of separate spaces from one another. And when you communicate between them, it's like distributed processes running on different machines effectively, although they are virtual, but it's all has all the same implications. So you need a process model that accounts for that. And actors is one natural choice here. So what are actors? Actors are kind of like objects, if you want, but where messages are always asynchronous. So like with objects, state is encapsulated in an actor, so you cannot access it from the outside. The only way you can access an actor is by sending a message to it. But unlike like traditional objects, messages are really one way. So you can just send a message to an actor telling it something. You don't get back a reply. If you want a reply, then that has to be part of like the protocol you program, where the actor you send the message to sends some message back to you as a reply, and that will be a separate message. And part of this model is that each actor has like an incoming queue of messages, and only one message is like taken out of this queue at a time, and this will be processed atomically. So all methods, if you want, are always synchronized, like in Java terminology, right? Every execution is atomic. Moreover, if executing or processing some message sends out other messages, then they're not actually sent out immediately. They are only sent out after the current one has fully processed. Including that if processing failed for some reasons, there was some abort or something, they are actually not sent out at all. So you can roll back and pretend these messages were never sent in the first place. And why are actors a good model for concurrent and distributed programming? Well, they have a couple of nice properties. So first of all, because all communication is asynchronous, it's like by definition latency agnostic, right? You never block on anything. You never assume that you get an instant reply. Any reply will be another message that you receive at some later time. And that later can now be arbitrary, and it's kind of, you're agnostic to how much later it is. And the maybe somewhat less obvious properties are that this model is deadlock free. Because you're never blocking on replies or anything else, there is no blocking. There can be no deadlock either, right? You're never waiting for anything. So when you're like conceptually waiting for a reply, what you really do is, well, you have other messages coming in, and one of these might eventually be the reply you're expecting, but you're not actively waiting for it. And you have to program your application in a way that this works. You're essentially forced by construction to do that. And similar, there cannot be any races because, well, first of all, there's no shared state. All shared is encapsulated in a single, in an individual actor, and execution in any given actor is always single-threaded, right? As I said there, it's always atomic. So there cannot be any race in that sense. There can be things like, you can still have similar phenomena on kind of like a level up if you want, and if you're not careful, but on the primitive level of the computational model, these things cannot come up. They can only come up on a like protocol level if you make additional assumptions about certain protocols between multiple actors. So you have to be careful how you define your protocols, but of course that's unavoidable to some degree. Well, and now that I've explained what actors are, I suppose the idea is obvious that our applications are now actors, right? So every application is an actor or actually a set of actors, and the interface of an application is just the messages that this actor understands. And messages can either be sent between actors, or they can be sent from the outside or to the outside, and that's how you actually invoke something on the chain. So for example, if you had an application that implements some service, then you could have a web page that sends an ingress message to one of these actors to invoke a certain service, and that might eventually send back an egress message as a reply. But there's more to it actually. So one thing that actors also allow is that you can dynamically create them. So actors can create other actors. And that is important as well, because it allows, like, first of all, more like dynamic process structures, right? So you can do something like spawning a new computation in an actor. And that is important if you want to be scalable, and also if you want to be configurable in certain ways. So for example, you could imagine an actor that implements some kind of database. And as I said, there's currently like a 4 GB limit for the memory in any given WebAssembly module, and that implies in a given actor. But you can distribute the state of a database across multiple actors, and you can just dynamically spawn a new one, new subnode of your database if you run out of memory in a local one. So you can use this to have more memory than a single actor would provide. You can also use it potentially to get more concurrency, because at least conceptually, messages to different actors run concurrent to each other. And depending on how the blockchain is implemented, this might actually be physically concurrent even, especially if they're on different shards. But even on the same shard, there could be some concurrency potentially in the implementation, although you can't rely on that, but you can hope for it. Yeah, and there are various other use cases. I don't really have time to go into why you would want dynamic actor creation. So like for user agents and things like that, which are dynamic. But yeah, hopefully you can imagine use cases. So to sum that up, yeah, actors are kind of like a notion of process that is particularly suitable for this setting we have here, which is a setting of distributed computation. And particularly because messaging is asynchronous, it kind of automatically accounts for the latency that can be inherent in communication between multiple contracts or actors. And it has these properties that it can prevent deadlocks and races, and you can create actors to reconfigure or adapt your dynamic program structure in various ways. Yeah, and there you have it. So those are like the three main ingredients. Here's like a summary, and at this point, it probably comes to no surprise that what I was describing is roughly what we implement in the DFINITY network, right? So this is kind of like a very high-level overview of what DFINITY actually does, with some minor details and some things we haven't really done yet, but like where we want to go. There are also various things that you have to do to make this really fly in practice that I haven't talked about. So here's like a little slide mentioning some of them. So especially if you really want it to be scalable, there are many more things you have to do. And some of these I'm not at all an expert on. So obviously you need much faster finalization than you have on something like Bitcoin or Ethereum. And on top of that, even if you have fast finalization, which like for DFINITY is around 1 or 2 seconds, that is still too slow for various applications. So on top of that, we have a notion of a query, which is kind of like an ingress message that doesn't use consensus. So if you don't need to modify the state, if you just want to query the state, then this is often good enough. And if you want the guarantee that the reply is correct, then you can still go through consensus. Another very important thing is, and this might be unorthodox to some blockchain folks, is that it's very important that you kind of drop this idea that blockchain history should be kept forever. that just obviously doesn't scale, right? At some point you have to cut off the history and throw it away. Otherwise you will just accumulate garbage forever. And so how this works in practice is that you have the running replicas, and they have cache the states of all active apps. And when a new node enters the network, it can just get a copy of the state from one of the existing ones in a signed way, so it knows that it's correct and it's not handed something bad. But it doesn't have to rerun the history. You never have to do that, at least not from the beginning. That just wouldn't work. Another interesting thing is that you want to support is that sharding. You want to make that more flexible. So you want to be able to configure different or diverse replication factors. So you want to have chains that are cheaper, which have a lower replication factor because you don't need as much trust or tamper-proofness maybe for your application. And ones where it's really important that this is absolutely tamper-proof and where you have a much higher replication factor. And then it becomes part of your cost model, like how much replication you request. Another thing which I didn't go into here, but which we haven't really done yet, but I think is important, is that so one thing we have is that we have a gas model where not the caller pays a call, but actually the actor itself has kind of a gas tank and calls for it, and can then implement its own pricing model to acquire payments for that, but the gas comes out of its own tank. So this puts away with some of the restrictions, but not all of them. One you actually still have is that, like, the call, an individual call is still bounded by the current block, right? So you cannot overrun a block. And that is still a very severe limitation that you somehow want to get over. And the idea there would be that you can actually overflow a block and continue a computation in the next block if that actor has enough gas in its tank. So it can keep running in the next block. So this is kind of like time slicing, or I call it gas slicing here, which isn't really a term, but just as an analogy. And then other things, you have to solve the problem of upgrading that I alluded to, and you need governance layer, which is a whole different problem, but which I'm not going to talk about here. But all these things are also important to actually have a scalable platform to implement this vision of general purpose computation. And yeah, I think that's about it, all I wanted to say here. And I'm happy to take questions.